Imagine two people using AI to build software. Neither of them reads the code, and neither of them conducts a manual review before the software runs. The first is a hobbyist on a beach, telling an AI agent to build a simple tool that converts PDFs to text. They judge the results solely by whether it works when they try it. The second is an enterprise team that has eliminated human code review. AI agents write the code, and AI agents test it. This software manages security access for thousands of corporate customers. On the surface, these workflows look worlds apart, but strip away the scale and we are left with a single unsettling question. Are these two people doing the exact same thing? Structurally, the practices are identical. Neither builder verifies the output. The only difference is the catastrophic stake of the outcome. Traditional maturity models fail to capture this risk. They usually view the hobbyist as a beginner and the automated enterprise team as the cutting edge. In these linear models, removing human intervention and scaling autonomy is treated as an advanced state, a level 3 achievement, on a path toward perfect efficiency. This staircase is an illusion. It hides structural failures by suggesting that any increase in speed or autonomy is inherently an increase in maturity. We need to replace the latter with a more honest framework, the configuration space. You aren't climbing a level, you are occupying a position. Success in this space requires a coherent configuration, a state where your development practices are proportional to the consequences you are accountable for. Evaluating development through these specific coordinates allows leaders to identify systemic risks that remain invisible when we only measure velocity. We plot these positions using 5 distinct dimensions. The first is the human cognitive role. This tracks the builder's contribution from manual coding and line-by-line review to designing the verification systems that check all outputs. The next two are quality evidence and verification mode. These measure the shift from reading code manually to trusting automated tests, AI verification swarms, and statistical defect rates. The fourth is the consequence domain, the actual stakes of a failure. This ranges from a minor personal inconvenience to security breaches that threaten lives or safety. The fifth is creative agency. This tracks where the builder's energy goes, whether they are reactive, spending their time fixing what broke, or generative, opening problem spaces that didn't previously exist. These axes reveal a core constraint for operational safety. The sum of the human role and the verification mode must be equal to or greater than the consequence domain. If we apply this to the enterprise team that removed code review without building new verification systems, their oversight score is 0, yet their consequence domain is at the maximum. Because their score of 0 is less than their high consequence level, they have no buffer against failure. This configuration reveals a state of ungoverned risk, structurally the same as the person on the beach, but at stakes where that practice is catastrophic. On the other side of the chart, we find teams that attempt to maintain safety by forcing humans to review every line of AI-generated code. This creates a biological bottleneck. Cognitive load theory suggests the human brain can only process about 4 chunks of information simultaneously.
Supervising multiple AI agents forces the brain to parse unfamiliar output it didn't create, effectively doubling the cognitive load. Running 4 agents in parallel quickly exceeds human working memory capacity. This results in supervision fatigue. Developers report significant cognitive fog and impaired decision-making, which researchers compared to the mental exhaustion of high-stakes gambling. Historically, software engineering has spent 50 years trying to solve this problem. Tooling was designed to reduce the friction of typing and implementation, not to create a massive new burden of reading and review. To sustain this work, the human role must evolve. Builders must move away from line-by-line inspection and toward the design of high-level verification architecture. Treating engineers as spell checkers for AI agents is an architectural failure that guarantees cognitive collapse. Then there is the idealist who trusts too quickly. They grant the AI full autonomy and remove human review to maximize speed. Initially, it feels productive, but as bugs and security vulnerabilities inevitably appear, their energy is consumed by firefighting, causing their creative agency to crash. This cycle is driven by the normalization of deviance. This is a social phenomenon where a team repeatedly skirts safety protocols without an immediate incident. convincing themselves their reckless approach is safe. In AI development, shipping without verification can work flawlessly for months, right up until a catastrophic breach occurs. The statistician W. Edwards Deming warned that you must build quality into the process first. Only after the infrastructure is in place can you safely cease manual inspection. The absence of failure is not evidence of safety. It is often just evidence that you haven't yet reached the edge of what your configuration can withstand. Sustainable AI adoption requires the configuration flywheel. It begins with configure, setting coordinates on the 5 dimensions. During build and verify, teams generate code at AI speed, but confirm quality through automated channels. Finally, they safely evolve into higher autonomy. To protect this flywheel, teams are utilizing advisory agent systems. These systems are designed with a zero blast radius. They can analyze context and recommend configurations, but physically cannot execute destructive actions in production. Turning this flywheel transforms AI from a source of chaos into a governed system of compounding organizational memory. This leads to the final stage, generate. Software contains 2 types of difficulty. Accidental complexity is the friction of tools and syntax. Essential complexity is the irreducible difficulty of specifying logic and solving the actual problem. AI can eliminate the accidental complexity of typing code. However, wasting freed capacity on doing the same reactive work faster results in only marginal gains. High-agency teams redirect that energy upward. They use their bandwidth to tackle essential complexities through compositional and generative design. The engineers who thrive are those who stop writing individual lines and start designing the vast verification systems that make human code review unnecessary. Engineering leaders must decide between chasing unguarded velocity or enforcing the coherence necessary to sustain it. The ultimate indicator of success is a coherent architecture that empowers developers to work at their highest generative capacity.